In 1972, astronomers Carl Sagan and George Mullen raised an issue regarding the Earth and the Sun, which later became known as the faint young sun paradox. Roughly 3 to 4 billion years ago, early on in Earth's history, the Sun was expected to be only 70% as bright as it is now. However, although the Earth was expected to be frozen based on the reduced output of the Sun at the time, liquid water was observed, leading to life on Earth. How was this possible? The Sun has slowly brightened over the past few billions of years, causing the surface of the Earth to warm up, and this process is known as radiative forcing. However, around 2.5 to 4 billion years ago, also known as the Archean Age, the temperature on the planet was expected to have been too low for liquid water, but this was not the case. A question you may be wondering is, how exactly do we know that there was liquid water back then? One of the pieces of evidence that supports this fact are zircon crystals. Oxygen isotopic compositions in certain zircon crystals suggests that there was indeed water on Earth 4.4 billion years ago. In addition, fossil records suggest that life on Earth emerged a few hundred million years later, and liquid water is an essential ingredient for life. Along with the issue Sagan and Mullen raised, they also provided a potential solution by suggesting that a greenhouse effect was responsible. Majority of the sunlight passes through the atmosphere to heat the surface of the Earth. However, some of that energy is reflected towards space, which can sometimes be trapped in the atmosphere by certain gases. This causes the Earth's surface to warm up even more. This is the greenhouse effect, and the gases that trap the reflected energy are known as greenhouse gases. Sagan and Mullen most specifically mentioned ammonia as the greenhouse gas that caused the Earth to heat up. However, although ammonia is a pretty effective greenhouse gas, it is destroyed by solar ultraviolet radiation quite easily in the atmosphere. There was an argument for ammonia which claimed that a photochemical haze would have stopped the gas from getting destroyed in the atmosphere, but a test using a model determined that this was impossible. This took ammonia out of the discussion. Carbon dioxide as the potential greenhouse gas is a more accepted theory. Carbon dioxide is one of the primary greenhouse gases of the current planet's atmosphere, and some believe that it played a similar role 3 to 4 billion years ago. One of the important factors to consider when talking about an increased carbon dioxide concentration in the atmosphere are asteroid impacts. Earth was bombarded with numerous asteroids early on in its life, and although the planet would have been an hostile environment for life in the short term, it does lead to an increased surface temperature over time. As asteroids crash into Earth, they are expected to have created lakes of lava by melting rocks with their impact. This lava is thought to have produced high amounts of carbon dioxide into the atmosphere. The impacts also deliver large quantities of sulfur, which is one of the essential components for life. Volcanoes are also seen as another source to produce the required carbon dioxide needed to help keep Earth warm. One of the problems with the large greenhouse effect theory is that extremely high amounts of carbon dioxide was required to heat Earth up enough for liquid water, and evidence of this is not easy to find. However, although we don't have reliable carbon dioxide measurements from 4.4 billion years ago, there is evidence that suggests that there was quite a lot present in the atmosphere around 2.7 billion years ago. From assessing the composition of meteorites that passed through our planet's atmosphere at the time, scientists estimate that the carbon dioxide concentration could have been more than 70% as opposed to the 0.04% in our atmosphere today. If this was the case less than 2 billion years earlier, it is possible the high carbon dioxide levels would have kept the Earth warm enough for liquid water. Methane produced by single-celled anaerobic microorganisms, in addition to carbon dioxide, could have also contributed to a warmer climate. Another one of the theories is that the Sun lost some of its mass from strong solar winds in the period of 1 billion years, meaning that the Sun could have had more of an energy output than the predicted amount. However, records show that although there was an increase in the rate of solar winds, they only lasted for an interval of 100 million years. This suggests that although the loss of mass from the Sun may have contributed slightly to the increased energy output at the time, it doesn't solve the faint young sun paradox by itself. The albedo effect is another theory put forward. You are probably aware that dark surfaces absorb light more than bright surfaces, and that opting for lighter colored clothes during the summer is a better idea. This is the albedo effect. Some suggest that a lower surface albedo at the time could have resulted in the temperatures required for liquid water. The faint young sun paradox gets even more strange for Mars, as although the planet is even further away from the sun than Earth, the surface of the planet shows signs that there was oceans and river networks 3.7 to 4.1 billion years ago. It is likely that a greenhouse gas, most probably carbon dioxide, was responsible for the warm climate on Earth, quite possibly in combination with some or all the factors that I mentioned before. But our planet's early history needs to be studied further and better understood to provide a more conclusive answer as to why Earth was warm enough for liquid water at a time it was expected to be frozen solid.